Okay,
Yeah.
we have a group here, so we'll start. So it's a great pleasure to introduce Professor Rick Eason. And he recently retired from the Department of Electrical and Computer Engineering in our university. and because he retired, he's now off doing a lot of things that he's very passionate about. Most recently, climbing Mount Everest, Mount Kilimanjaro, as you no doubt just heard in our discussion. But throughout his career, he has traveled quite a bit. He's worked in Japan, Malaysia, no doubt several other places. And he's worked on many different things, but the one that's probably of greatest relevance to CCI and potentially for involvement, and this is a presentation he's giving because he would like to become involved in CCI, and we definitely want him, is his involvement in high altitude ballooning, in which he has included students in the design and building of the payloads. And I think there will be some potentially very exciting opportunities for airborne investigations through our collaboration with Rick in the coming months and years. So with that, I'd like to turn it over to you, Rick, and we look forward to having you involved in the Institute and hearing more about your adventures as you travel in your retirement and work with us.
Okay, yeah, well, thanks. Yeah, as you said, I just retired, and and it wasn't because I was tired of working. It's just because I wanted to be able to do different things, recognizing them. I'm getting older. So talking with a couple of people in CCI, and Paul suggested this association. So I said, well, what the heck, I'll see what it's about. Maybe try it out. So I did give a talk here 4 years ago on high altitude ballooning. So I'm going to kind of give like abbreviate through that, but then talk about a few other things that I've worked on over the years. And so just try to get through here. So with high altitude ballooning, this is also known as scientific ballooning. Basically, it's a weather balloon with a gas, carry things, experiments, cameras, et cetera, up into the stratosphere. Our typical balloon payloads look something like this, and you can get balloons that, they're huge and carry thousands of pounds, and up to 1,000 or more pounds. But we're working with these small ones. Basically, we've got a latex balloon. We do use one that's a bit larger than the Weather Service. There's a parachute down below it. We can include a radar reflector, and then these payload boxes, one or more of which would have tracking equipment so we can follow where the balloon is, and the rest have experiments from either our students or I've been doing a lot of launches with students in the state. I've got one scheduled for Wednesday down in Maine, for example. But so a typical flight will lift payloads up to several kilograms total. The FAA regulations say that you can carry up to 12 pounds without having to do a lot of paperwork. And so you can go more than that, but it involves a lot of rules. If it's under 12 pounds, it's just like letting your party balloon go. You don't contact the control tower or anything. We do, you can, but you don't have to. But regulations are a lot easier if you stay under these limits. We fill with gas. We try to ascend about 5 meters a second. It does have a near constant ascent rate, and we've gone up to 35 kilometers, a bit, most of the time, it seems like. The balloon expands to about 10 meters or so in the less dense air, and then until it bursts. By that time, the balloon is maybe 10 meters in diameter or more. Then it descends by parachute, maybe 30, 45 minutes, and we recover the payloads. And we generally launch in the morning if we can, although we've done a couple of night launches. Typical flight profile for these balloons for what we're doing is, it has constant ascent rate, pretty constant. As it goes up, the ratio of the density of the air inside the balloon to outside's the same. It gets bigger diameter, so it's got a bigger surface area, but then the air is less dense. So anyway, it tends to go up about constant rate. It gets up to, in this case, this is one of our highest flights, on up 35. This is way up in the stratosphere. And then the balloon bursts and it comes down. Of course, the parachute's deployed automatically. It's just right there. The air is less dense, so it falls faster, and then it slows down. In case you're not that familiar with the atmosphere up there, we've got the troposphere down below, and this is all defined by the, let me get this out of the way if it's in your way, but the temperature profile defines these layers of the atmosphere. So in the troposphere, the temperature decreases typically, and I'm going to use mixed units because I'm a pilot and pilots do thousands of feet and degrees Celsius, but it decreases, temperature decreases about 2 degrees Celsius per 1,000 feet. And this is pretty constant linear relationship until it gets to 10,000 meters or so. And then you get into what's called the tropopause, where the temperature doesn't change too much, and then the temperature starts increasing. That would be the stratosphere. Levels out again, then starts decreasing. That's the mesosphere. Then it goes up to thermosphere, and then up above that's the exosphere. So anyway, we're launching our balloons on up to about 35 kilometers or more. And so we're up here, well, it says weather balloon there. Kind of see where we're at in the atmosphere. Of course, the pressure decreases. This is altitude on the vertical axis in kilometers. So down at the ground, we're about 1,000, a little over 1,000 millibars. And up there at 100,000, well, we're more up at 35 kilometers. But anyway, we get about 5 millibars or so. So it's 1/200th the pressure. UV, of course, increases on up there, but the UV attenuates in the atmosphere. So there's UVC, A and B. I stole this from somewhere, but kind of see the different frequencies there attenuate at a little different rates. So why we do this altitude ballooning, our cost is, well, if you want to send a satellite into orbit, if you wanted to do that, it's, $100,000, a couple $100,000 just to send one little 10 centimeter cube. It didn't cost us hardly anything to do these balloons. So the marginal cost of sending a payload with that size thing can be tens of dollars, and we put several of these on one balloon. So the whole balloon flight itself might cost, some hundreds of dollars. We tell this to school kids, the environment up there is similar to Mars. The temperature, pressure, radiation would be similar to what you get on Mars, and you can just kind of do some experiments there. So students will send up seeds or whatever and see how they compare to seeds that didn't go up. And some of the examples here are things that school kids might be doing for experiments. In terms of what it's like to do a HAB flight, kind of go through a few of the steps here, the prediction, preparation, etc. So we have prediction software that usually when we do the launch, we don't want it to land out in the ocean. I had the opportunity to go to Mauritius a few years ago, and I gave a little talk on ballooning while I was there. And so here's a prediction I did there, just say, hey, it's possible it lands back on the island here, not always out in the ocean. But so the prediction will just tell us on a particular date and time, then where's the balloon gonna land if we launch at that time with this rise rate, et cetera. We usually string our payloads the day before or a couple days before and just have the boxes ready to go, batteries charged, everything ready to go. And especially if we're doing a launch at a school, we can't do everything right then, but we'll bring it out and get everything, batteries turned on, things turned on, plugged in, boxes taped up, et cetera. And then we fill the balloon with gas. And say they're pretty big balloons here. I usually try to involve the students as much as possible when we're doing this with schools. And then tying it off here, then we're ready to launch, and goes on up and off and away, and then up into the stratosphere, hopefully, and then the balloon will pop and comes down somewhere. And going on up, the sky gets completely black. It's just like you're in space there, but you do have a line of blue atmosphere there. This curvature here is not all the curvature of the Earth. There is some curvature that's visible, but this is mostly the fisheye from the camera. If the camera pointed down, the fisheye would go kind of look like a bowl-shaped Earth. But anyway, that's about as high as we get there up off the coast. And I had a few burst sequences here. I took some out because I couldn't cycle through them as fast as I wanted once I got the presentation in presentation mode. But anyway, that's a balloon burst. And parachutes deployed, like I say, it's right there as the thing starts to come down and comes down land somewhere. And we have tracking software so we can find out where it is. This is probably not a good picture to show because it seems to indicate that this thing always lands like on a road, and that hardly ever happens. It's usually off in the woods somewhere, but this particular one landed pretty close to Route 9. In Maine, it's almost always in a tree, so they're up pretty high. We do have these long poles that we can go and reach it. I cut the strings and pull them down or grab onto them or whatever, but with 120 launches now, I've never lost a payload, so we've always managed to get them back. Sometimes, of course, in Maine, they'd be in the lake, so it requires going out on a nice little canoe ride. This one here, sometimes it gets tangled up. So this one landed right on the shore, actually, but it was on an island. So I still had to paddle about 4 miles each way. I think it was an 8-mile canoe trip to get this one, even though it was on land. Sometimes the GPS doesn't work, so we always have a little backup beacon that just sends a beep, beep, beep on the radio. We can pick it up there. We can only pick this up on the ground a mile or so away, but I'm a pilot, so we jump in the airplane and fly around and we pick up the signal, and then we can go in on the ground and pick it up. So this has saved us probably a half a dozen times when GPS things weren't working for one reason or another. So just kind of a quick summary here. We started in 2011. This was the Maine Space Grant Consortium actually came to us and said, hey, do you want to do some ballooning stuff? And I found out they had money, so that's kind of how I got started. I didn't know anything about it before that. They give us good funding. We do roughly 10 launches a year now. Done 120 so far. I'm actually counting 2 launches I did in Hawaii with this guy that he launched one there and lost it. And then when he went back summer before last, he said he was going back to do a couple more launches with this summer science camp. I said, oh, I'll go with you. So I helped him with those and we got those back. Do a lot of them with the schools. And there's an Eclipse launch we did in 2017 that Montana State led this project. And we were part of that. And there's an eclipse coming up in 2024, and Montana State wanted to do another project. And instead of having them do all the work, training all the teams that were doing this, there were 55 teams last time. They're planning to have maybe 80 of them or so this time. But instead of them doing all the work, they decided to break up into pods, and they asked if we'd be one of the pod leads. So we're going to be actually training 8 of the teams and doing that launch. It's going to come through Maine in April of 2024. So anyway, that's a project I'm still working on. This is an old chart from way back when. I hadn't done too many launches, but you can kind of see that we launch in one place and land in another. A few of them have landed up here in Canada. But like I said, this is back when we only had like 30 or 40 launches under our belt. So anyway, like I said, I kind of talked about this 4 years ago at the Climate Change Institute. So just to tell you a few of the other things that I've done in the EC department and just on my own, sort of. Robotics, embedded systems. Mostly that's with the ballooning, but anyway, robotics, I'll mention just a few things here. One of them, although this is ancient history, I'll tell you what my PhD thesis was on, which really got me, the funding was there, so that's why I did it in robotics. I was really more a logic design guy at the time, but anyway, go through some of these things. Multi-sensor fusion was on what my PhD was. That was really on localizing, determining the position and orientation of an object from multiple sensor inputs. So you might have a touch sensor that touches the surface. I just got a really simple 2D example here because I think it's pretty easy to understand from this perspective. If you wanted to like determine where this edge was, you just kind of fit a curve through that, fit a straight line through it. You got to modify the traditional method a little bit because it's not just y equals ax plus b. You want to make it so it handles vertical lines too. But anyway, that's the idea. So if you wanted to determine where this edge was, you can fit points through that. But if you have points on multiple edges, okay, well, I was working with doing this. It's kind of extending the approach. But you might also know, for example, where vertices are. I know where this vertex is. And there's some error that says I know where it is in this direction better than this direction. So I'm incorporating all this into it. We might have where I know that this vertex is on this line. So for example, you have a camera here and it just sees the vertex out there, but it doesn't know how far away it is. It just knows it's somewhere on that line in space. So that's another type of data we might have. And you might even have a line, an edge of an object, and you know it kind of lies somewhere on a line. It's like if the object is sitting on that edge. And again, this is a 2D example. My work was all with 3D and with points, lines, and planes, and they were all observing point features, line features, and plane features of an object, total of 9 possibilities. So I went through and developed all the math for how you kind of work with that. It was kind of the least squares thing with Lagrange multiplier. So point is, it's kind of a lot pretty math heavy, but it was also implemented in software, Fortran at the time. One thing a little more recently is the Dexter shoe company came to us. This has been 20 something years ago now, but they were trimming the soles of shoes. And part of the process is they have a human operator that would take the shoe, and there's a high-speed cutter running at 10,000 RPM, and they just take the edge of the shoe and kind of trim the sole. And so it was repetitive motion, high-speed cutter there. OSHA really wanted them to automate this, so they came to us to see if we could build a machine that would do this. And there was another faculty member in the department at the time, and he said, well, okay, I'll do the hardware part. He designed the motors, all the hardware part, and I did the software. So what the machine we ended up with was a 4-axis machine. The shoe gets clamped onto there's a clamp, moves back and forth on this, what we call the X direction, moves in the direction from heel to toe. The cutter moves back and forth on this blue piece, perpendicular to that, and we call that the Y direction. And that gives it 2 degrees of motion. And then also the bed would tilt a little bit. It's so that it could, it's pivoted off center a little bit, so it could raise up and down just a little, just so the cutter could be at the right height on the shoe. And then the blue part there would tilt forward and backwards so the cutter could stay perpendicular to the direction of travel. Anyway, 4 axes of motion. I did all the software here. It's probably 15,000 lines of code. It was a lot of code. Dexter built 14 of these machines, and I heard they were trimming over 1 million pair of shoes a year with them. Then when they decided to sell their operation to China, then the machines went to a company called Allen Edmonds that makes $200 and $300 a pair of shoes, maybe $400 and $500 now. And they just wanted the machines because they could do it more accurately. Allen Edmonds had tried to develop a machine like this, paid somebody like $250,000, and they failed. So anyway, they used the machines. Thought that was a good success. In terms of teaching of robotics, I've taught undergraduate robotics every year for about 3 decades or more. And then graduate class was every other year. Much of the focus in the undergraduate class was on kinematics. That is, if you know the joint angles for an arm, how do you figure out where the end effector is? You know all the joint angles. Inverse kinematics, if you know where you want to put the end effector, how do you make the joint angles? Trajectory planning, sensing. Graduate work, most of it was on computer vision, but also did stuff with neural networks, fuzzy logic, genetic algorithms, a few things like that. Just one thing that was kind of recently, so in terms of these kinematics, there's you can see, here's the robots we have in lab, and the students with a focus on kinematics in the class, they would have to, from scratch, write software so they could okay, I want to move the robot to this XYZ position, then what are all the joint angles? And there's a series of labs that they would go through, kind of work up to it. The lab before the last one, they'd have to pick up a block and then move and raise up in the air, move in a straight line, then set it down. And then for the last lab, they would play this puzzle called Tower of Hanoi. And if you're familiar with it, it's the traditional version has 3 pegs. I'll go back. Has 3 pegs, and there are discs on each of the peg. The discs are different sizes from smallest to biggest, with a hole in the middle. So they sit on the pegs, and you have to move the discs from one peg to another peg, and you can only move one at a time, and you can never put a bigger one on top of a smaller one. Well, with the robot, it's easier just to pick up blocks. So we had blocks of different sizes in 3 piles, and here's like the robot. Whoops, wrong direction. Here's the robot in mid-play here. Okay, my computer's really slow here. I'm not sure. I'm going to try one more time. So it's picking up the silver block. It's going to put it on the blue one, and then it can pick up the yellow one, put it on top of the green one. Then it can take the silver one, which is over here, and put it back in the middle. And then it can move the blue one over to this now empty stack over there. Anyway, so this is what the students would do, writing their code in C and then telling the robot to do the moves. When COVID hit, I'm wondering, okay, here's a big part of my class. What am I going to do for the students because they can't come into lab? So what I did is I went into lab, measured the dimensions of the robot. Well, actually, I spent the first few days trying to find a simulator, robot simulator that would work, kind of work it into what we were doing, and I wasn't happy with anything that I saw. So I spent a couple of weeks writing my own simulator, and what the students will do is they just do the same code they would have done with the real robot. They just send commands to the simulator instead of the real robot. And so let me actually show you it running here. This is actually a student's code, and he has the first part of it. Well, all the previous labs, the last lab, he just typed 17 here. And so he wrote the code to control my simulator, and just sending moves to, okay, have this motor, it was stepper motors on these robots, have this motor step so many steps, this one steps so many steps, etc. And I did the code to do the robot motion in about 2 weeks. And then it took another week to get the picking up blocks and straightening them up in the gripper. And if I let go of the block up in the air, it falls to the ground, etc. Notice it does lighting. It actually, and I can change my viewpoint. I can look from the right or move over to the left. I can move up and down, and I can go in and out, change my camera viewpoint like that. So students can just running the simulator instead of the real robots out in the lab. So this is actually one of the students' code that he wrote to do the last lab. When we came back on campus, I actually took his code, recompiled it with the real robot. I just changed one line of code so it was sending commands to the real robot instead of the simulator, and it ran. I mean, that was actually the code that you're looking at. I mean, in the picture I did right. I'll go back. This picture right here is his code running after just having written it for the simulator. It worked well enough that the next year, when we were doing hybrid classes, I gave students the option of using the real robot or the simulator, and half of them just picked the simulator because they didn't have to come into the lab to do it. Anyway, let me go ahead and stop that one. So let's see. That was one, like I said, I'm kind of proud of myself for getting that one accomplished in the short time that I did, and then everything just worked. Just kind of, I'll show you. I don't have much on slides for embedded systems and stuff. That's kind of what we do with ballooning. But I have Raspberry Pis and Arduinos that I like to play with. I got like 5 Raspberry Pis running at my house. 2 of them have cameras on it. One of them, it's like I wanted to. If an aurora comes, I want to see the aurora, the Northern Lights. You can sign up for space weather at $5 a month. Well, I thought, well, I have one of my Pis just every 30 minutes it goes and queries a website and scrapes the data, and then it'll send me an email if the probability of an aurora gets up higher than a certain percent. Anyway, just as an example. And actually on the side too, I'm a kind of compulsive programmer. And one thing I like to do is collect mechanical puzzles. So I've written a lot of programs, software to solve puzzles. And so I'll just show you this. If you could just Google Rick Eason puzzles, you'll see my website here, and it shows some of my designs. And some of these are actually made commercially or have been made commercially. They'll click on there and it just says, once the description comes, oh, there it goes. Designed by Professor Rick Eason at UMaine, Orono, et cetera. So a few of these are out there. One of them I did most recently, this logical progression. This one, this is one I like the best because it's 16 pieces. And if you use logic, you can actually solve the whole thing without any trial and error, which is kind of different. But so anyway, and I just got to show you, I got 5 out of 5 stars from the 8 reviewers there. So anyway, really into writing software for this. I've actually got, there's one over here. This is one that somebody was working on. Most of these puzzles are my designs, but I was helping a couple people earlier this year on coming up with configurations for some of their ideas. This one, the guy had the idea, and I told him this particular configuration, wrote software, and he might do this one commercially. He's pretty prolific and has his contacts. So anyway, puzzle design and using software is kind of one of the things I really like to do. Just some other things about me. I like to do stuff. So I'm a private commercial pilot. I actually am a flight instructor, CFII, so that means instrument instruction. I have my own airplane. I've flown to California twice and also to other trips too, shorter, but all the way out to California 2 times. I am a Part 107 remote pilot, although I don't do a lot with it, but this is drones. It's easy to get your Part 107 if you are a pilot. So I've got an amateur extra ham license, and I have required my students to get their license in the ballooning, because we use that with quite a bit, both in the woods and also with the balloon. And because of that, I'm a volunteer examiner and give the ham exams right here on campus with the students. I didn't put down here, but I am a PADI scuba advanced, but I haven't done that in quite a while. But anyway, I got 7 patents, several foreign ones. Been to about 50 countries so far, all the states multiple times. Hawaii is the only one I've been to just twice, I think. But most of them half dozen or dozens of times. I also enjoy camping, hiking, biking, canoeing, like I say, puzzle collecting, designing, contra dancing when we could do that, playing music, etc. I just like to do stuff, and that's one reason I wanted to kind of check out the Climate Change Institute to see if there's maybe some interesting opportunities here, maybe have some interesting experiences, etc. So not wanting to keep this too long, I'll just open it up to any questions or whatever.
Well, thank you, Rick. That was very exciting. I'm sure there'll be other questions, but if I may, I'd like to start with 2. The first is a joke question. Okay. So did you visit all 50 countries and 50 states remotely, or actually go there?
Okay. This is always in person, yes. And when I said the 50 countries, I'm not even counting the ones that I changed planes in. Like I came back through Ethiopia and Sweden, and I haven't really been to those for real, so I'm not counting those. So
okay, well, that was just kidding anyway.
Yeah.
So one of the things that that my group is heavily involved in is sampling, in particular, relatively small, sometimes relatively small water samples. Mm-hmm. But these can come from very remote places, and most often we like to climb up to high altitude places to collect them ourselves, go into extreme areas. But you can't do this on a regular basis, costs a lot of money and takes a lot of time. So there's a real advantage to things like drones that we have not yet used for actually collecting samples and bringing them back. But the disadvantage, of course, of drones is they can only go so far. And they can't always get high enough, and they can't always, in the case, for example, of heavily crevassed areas, go in far enough. So have you or other people managed to, first of all, I mean, other than a drone, let's say a combination of a drone and a balloon, would that be, is there potential in using the elevation and or ability to go far distances with a balloon coupled with a drone or something like it, basically like the old-fashioned dirigibles, to have direction and actually grab a sample and bring it back? Talking about a very light payload, an ounce of water.
Yeah. So yeah, I guess several thoughts come to mind. One of them would be the possibility of just collecting samples on the way up, but you can't control the direction of a balloon.
Right.
I have worked with, Alex Friesen. I don't know if you've met him, but he's over in mechanical engineering. He's actually had a couple proposals for some dirigible type balloons that they weren't funded, but we've actually thought about that for doing some stuff with like forestry here in Maine. Mm-hmm. One other thought here is that I've always been hesitant. I mean, I've heard that, okay, what happens is you can't have remote control stuff over 400 feet in this country. They got the rules there. You can get waivers for things, but I've kind of heard that anything that you have that could be in control is a problem, because if you lose contact, then it's out of control. So even have a balloon, for example, use a kite for the parachute so you can kind of steer it on the way down. We kind of looked at it, but we didn't really try to implement it. However, there is now a NASA competition for releasing a payload and having it return, a hard drive or whatever, having it release it from altitude and have it return to a location. That's kind of a competition that they're having. So I don't know, I'm gonna have to rethink about the possibility of doing something like that.
Well, yeah,
Like
maybe.
releasing it from altitude and having it fly back.
Right. I think we would have less of a use for that and more of a use for going down to a surface, picking something up and bringing it
And
back.
bring it back, yeah.
Yeah.
One
Maybe
thing
we
in
could
terms
talk
of
about it.
yeah, I was on a master's committee. I was on the committee for a master's thesis where the student was actually working with blade design for high altitudes. And he was mostly from a theoretical point, but I know that people are working on it, to be able to go up to higher altitudes.
Yeah, this wouldn't necessarily have to be super high. You're talking about elevations which are way above where we would collect a water sample
Of
from.
course.
So, the highest would probably be extreme would be Everest, 28,000. But in most cases, it's more like 6 to 15 or 18,000.
Yeah.
So, I mean, if you're interested, we'll set something up after this and maybe get together and talk.
Sure.
Thank you.
Yeah.
Others out there, I can't see everybody, so.
Can't see them at once.
Hey, Rick, this is Greg Zarro in anthropology. I just have a quick curiosity question more than anything else.
Yeah.
With the high altitude balloons, you mentioned several eclipse launches, and I'm just curious, is this for visual purposes only, or is there some data you're specifically collecting during periods of eclipse?
Yeah. So one of the main, so like I said, we had there's an eclipse in 2017. And what they did is they had 55 ballooning teams across the country. And one of the features of that was just, it was visual, just like we live streamed video from the balloon onto the internet, real time. Okay. So that was at least the idea with the project. Not all of them were successful, but you could go onto a web page and click on a balloon and see what the view looked like from the balloon at that time with the shadow coming across. So we're going to have a similar component on this next one is the plan, and we're actually helping develop, what we're doing. But there is one experiment in particular that they're going to be doing, which is gravity waves. These are not gravitational waves, but gravity waves were waves in the atmosphere. So we're actually going to try to have the balloons go to altitude and float so that they're pretty stable. And then you can detect it with the GPS, detect motion of the balloon during the eclipse and see what effects that might have. Those are, I think, the two biggest kind of goals that we've got, but we could also put other experiments on there. Yeah.
Great. Thank you.
Yeah.
It looks like Dan's one of our most techie faculty. So you have a question, Dan?
I do. It's to do with, again, conducting work in remote places. Some of the glaciers we go to are obviously heavily crevassed, and but before we can choose, a really ideal place to drill, we need to do GPR measurements, ground penetrating radar, to try and see the internal layers, see the internal flow, and sort of generally image the glacier. So what I was wondering, you may not know the answer to this right off the bat, but is it possible to do GPR from a drone? Is it possible to shrink down a radar system to the point where it could be flown over the glacier remotely?
I'm not familiar with that. How big are the ones that you're using now?
They, I think the ones I seem to remember from from Steve Arconi's gear, the boxes were sort of like a foot cubed in size, the antennas. Whether or not you need two of them, I think one might be a transmitter, one might be a receiver. So I think there may be two. So maybe you need two drones, but
Yeah.
I don't know. It's probably a challenge, but yeah,
Yeah.
just throwing that out there.
And just to jump in on what Dan said, the reason for this is that a lot of GPR is flown by helicopter and even by fixed wing. The fixed wing obviously has to move much faster. And once you get up to elevations above 6,000, 6,400 meters, helicopters, except under very extreme safety, medevac conditions don't go up there. So something else is needed. And it's also hard for drones even to get up.
Yeah, I imagine it'd be a challenge. I'm always amazed at what people can do, but because of the you can always build bigger drones, and there are waivers you can get for flying out of the spec of the regular size drones and things. But yeah, doing that at altitude, it's hard for me to say right off here.
Yeah,
how possible it is.
All right, maybe we can get together at some point and try and do some calculations, see if it's even possible.
Yeah,
that'd be fun.
Yeah.
Anybody else out there? Okay, well, you obviously have gotten us thinking. We obviously have some ideas and which obviously don't have simple answers. So
yeah,
we'll look forward to, maybe 3 or 4 of us getting together and next time you're in Maine and seeing what we can talk about, because I think you obviously have some expertise that is way outside of our range of expertise. So we might be able to do something very exciting together.
Yeah, that's kind of my hope here. Is it's see what can happen here.
Wonderful.
And I am in Maine most of the time. My wife's going to see to that, but yeah, so just let me know. Yeah.
Okay, wonderful. Anybody else with any other? Oh, Cindy's clapping. Thank you. Thank you very much.
Thank you.
Take care, Rick. Have a good day. Great
Okay.
to see everybody.
Well, thanks for taking the time to hear what I had to say.
Thank you.
Okay.
Bye.